Hi everyone, welcome back. Today we're doing two sums, one question in the Blind 75 series question set. This question set is optimized such that these questions cover most questions that you see in technical interviews. And hopefully through this series, you're able to explore the various concepts that we need across various types of data structures as well as questions. So for today, we're dealing with an array question. And in this question, we're given an array of integers, nums, and an integer target. And we have to return the indices of two numbers such that they add up to the target. And to make it easier for us, for this question, we can assume that each input would have exactly one solution, and we may not use the same element twice. And finally, we can return the answer in any order, which simplifies this a lot for us. So for example, in the first test case given to us by Leetcode, we can see that the input is a linear list 2, 7, 11, and 15. And this is an ascending list where all numbers are in ascending order. But that is not the case, as we will see later in example 2. In this case, the target is 9. So we can see that the two numbers that add up to 9 is at index 0 and at index 1. So because 0 and 1 are the indexes, we return them in a list of size 2. For the second example, we can see that we're given a non-ascending list. The list is not sorted, and it's 3, 2, and 4. The target is 6, so in this case, the answer is 2 and 4, index 1 and index 2. For the final example, we're given a list of size 2, and this contains duplicates 3 and 3. But these two numbers add up to target 6, so we return them as 0 and 1, the corresponding indexes for both trees over here. And to solve this question, one approach that we can use is by doing a linear scan across these numbers. And we can also keep track of a cache that tells us what are the numbers that we've seen in the past, along with their corresponding indexes. And by doing that, what we can do is we can do a linear scan through this list. At each index that we have, we get the corresponding number, and we also calculate the complement or the number that we're looking for to get the target. So in this case, for example, if we are at 2, then the corresponding complement that we're looking for is 7. So we will check whether if 7 is inside this cache, and if 7 is not in this cache, we would just add this current number as the key and the corresponding index as the value, so that we can search for its index later on. We will then move on to 7, which is the next number. And in this case, the complement is 2. So we will check if 2 exists in this cache. And we can see, yes, indeed, we added 2 into our cache in the previous iteration. So we can return the corresponding index together with the corresponding index of that complement, which is 2, giving us 0. And we just return 1, 0. So that's not exactly the answer as said here. But because we're allowed to return the answer in any order, this solution works. So with that, let's quickly go through one simple example with the second example test case. So in this case, we have 3, 2, and 4. We initialize the cache, and this current index is pointed on the left element of this list. So what we can do is proceed with this algorithm and trace it out together. So the current index is equals to 0, current number is equals to 3. The complement that we're looking for to get to the target is target minus current number, giving us 6 minus 3 equals to 3. So in this case, we see that 3 doesn't exist in this cache. So unfortunately, we cannot return the answer in this iteration. So we would just add this current number together with the current index, so that hopefully future iterations can use this as the complement to return the answer. So now we move on to index 1. And the current number is pointing at 2. And in this case, this would be 6 minus 2, giving us a complement of 4. And we will check whether if 4 is in the cache. It doesn't exist, so, well, we can't return the answer in this iteration either. So we will add the current number together with the index here. And we will move on to the next element, which is index 2, current number equals to 4. Complement will be 6 minus 4, giving us 2. And we check whether if 2 is in the nums to index cache, and sure enough, it exists, so that we can return the answer in this iteration. So current index is equals to 2, and nums to index cache for this complement will be equals to 1, giving us a final result of 2, 1. So hopefully this trace makes it clearer for how this algorithm works. Now our final job is to implement this algorithm. So the first step will be to define the cache. So let's quickly define this cache as a map of integers to integers. Let's call this nums to index cache for readability. So the next thing that we will do is also define a vector of integers. This would be our answer. So let's call this answer. So now we are ready to do the linear scan from left to right to populate the nums to index cache or get the answer. So let's do int index equals to 0, index less than nums.size, index plus plus. And we can get the current number. This is of type integer. And this is equals to target minus, sorry, had a brain fog right there, but we are trying to get the current number for this given index. The next thing is to get the complement. The complement will be equals to target minus current number. And now our job is to check if this complement is inside this cache. So if nums to index cache dot find complement is not equals to nums to index cache dot end, then in this case that's our answer right there. So what we can do is we can do answer equals to vector of integers. We would just return the current index together with the corresponding complements index. So let's get the corresponding complements index by passing in the complement into the cache, and we got the answer. Else, if the complement doesn't exist in the cache, then what we can do is we can populate this cache with this given current number and assign this to be equals to index. So at this point, I also forgot to add a break statement here so that we do not have to waste additional computations. We have already gotten the answer, so we can break out of the linear scan to save time. So once we're done, we can return answer. And this is pretty much it. Let's do a quick check to see that everything makes sense. Looks great. Let's run this against some example test cases. It passes. Let's submit this. And there we go. We got the answer. Yay! So for completion, I'll also be talking through the time and space complexity of this algorithm. The time complexity, for new viewers who are new to this concept, the time complexity represents the worst case scenario of how your runtime scales with respect to the size of the list or input, in this case, the size of nums over here. So if you let n to be the size of nums, yeah, I need to get used to commenting in C++, but it's like this. So if n is the size of numbers, then we can see that the time complexity in this case, the worst case time complexity for this algorithm is O(n). And that's because we are doing a linear scan from line 13 to line 22. So if you have a list of size 100, then we will have to make at least like the number of computations that we have to make here would scale linearly due to this for loop over here. And for the space complexity, similarly, space complexity represents the worst case space or RAM that you use to run this script. So in this case, the space complexity is also O(n), because we're keeping track of the previous numbers together with the corresponding indexes that we have seen in this cache. So in the worst case, if you can only find the solution at the end of the list, then you end up having to store all numbers before the final element in the list inside this cache. So you will use up a lot of memory over here. Linear time, so still okay. Which is also explaining why my memory usage is like 22%. But anyway, this is one approach. Of course, there are other solutions, but I hope that this gives you a perspective into how you can solve tvsums using a simple cache. And this way, you can solve this solution in linear time, O(n), and with space complexity, linear space as well. So with that, that's pretty much the end of this video. I hope you liked it. If you have any comments, please leave them in the comments. And with that, I will see you in the next video.